We often refer to a standard temperature and pressure just so that we don't have to keep stating temperature and pressure all the time if we're going to use the same one over and over again. So standard temperature and pressure, also known as STP, is the temperature is 0 degrees Celsius and the pressure is that at 1 atmosphere. So sea level pressure and 0 degrees Celsius. All right, so since we have a standard temperature and pressure that we often use, we then, using the ideal gas law, have only volume and number of moles that are variable, so we can calculate for 1 mole of a gas what the volume will be. So we rearrange the ideal gas law to solve for volume, which is nRT over P. Okay, so at standard temperature and pressure, for 1 mole, we have 1 mole of gas times R times the standard temperature, which remember we have to put in kelvins, so that'll be 273 Kelvin for 0 degrees C, and divide that by 1 atmosphere. So your units will cancel and you will get 22.4 liters for 1 mole at standard temperature and pressure. And this is a good number to learn. It's not necessary that you memorize it. You can always calculate it from standard temperature and pressures, but it's a good one to remember. It can be very useful to know that volume without having to calculate it. This also allows us to easily calculate the density of any gas at STP. So let's pick carbon dioxide, and remember that density is mass divided by volume. And so if we're we can do it for 1 mole. There's no reason we can't do it for 1 mole. The ratio mass to volume will be the same no matter how many moles we use. So we can say it's equal to the mass of 1 mole, which is simply molar mass, divided by the volume of 1 mole, which we calculated up here for STP. So for carbon dioxide, the molar mass is 44 grams per mole, and the volume at STP is 22.4 liters per mole. So your units will then come out to be 1.96 grams per liter is the density. So you can calculate the density of any gas at STP easily using that the number for the volume of 1 mole. And again, you can always calculate it from the ideal gas law. You can always derive it if you don't remember what it is. All right, let's talk about stoichiometry using gases. We have previously talked about doing stoichiometry, which is using reaction equations to find amounts of things, and we always have to convert to moles. And we've had 2 ways so far to convert to moles. We've had grams, which you get to moles by dividing by the molar mass. And we've also talked about solutions where we have amounts in molarity and volume, and to get to moles you simply multiply the 2. And now we have a 3rd way to get to moles. We can use pressures, volumes, and temperatures, and we do this through the ideal gas law, where N is the number of moles and it equals PV over RT. So we can now solve stoichiometry problems of gases using something other than grams. So let's do this example. We have 5 liters of chlorine gas reacting at STP using the reaction given. How much iron 3 chloride can be produced? All right, so here's our reaction, and again we have to convert amounts to moles in order to use the coefficients of the reaction equation. So we have to convert 5 liters, which is a volume, and standard temperature and pressure to get number of moles. So the number of moles is given by PV over RT. So in this case we have 1 atmosphere at standard pressure. Our volume was given 5 liters. R is a constant. Liter atmospheres per mole Kelvin. And our temperature is 0 degrees Celsius, but in kelvins it's 273. All right, so from that we can calculate number of moles, and we get 0.223 moles of chlorine that we are using as a reactant. Now that we have moles of the reactant, we can get moles of the product. We take that number and we use the coefficients, and we say 2 moles of the product that we want per 1 mole of chlorine. And if we wanted to convert it simply to moles, we can just stop there and say 0.45 moles of iron 3 chloride. We could also go further and convert it to grams, but in this case it's not necessary. Let's do another example. When we have an automobile collision, an airbag fills due to this rapid reaction, which forms nitrogen gas very quickly. What is the volume of the filled airbag from the reaction of 130 grams of reactant at STP? So let's do the problem. We've got the amount in grams, the reactant in grams, which is what we're used to, but we want to know the product in volume. And we have a temperature and pressure. So again, we convert to moles in the usual way that we've done previously. Use the molar mass, which is 65. Then use your coefficients. We get 3 moles of nitrogen for every 2 moles of reactant. And that will give us the number of moles of nitrogen that we have produced. But again, we want the answer in volumes with temperatures and pressures, so we have to use the ideal gas law, solving for V, because we're asked for the volume. So volume equals nRT over P, which will equal the number of moles we just got, 3 moles. R is our constant. The temperature is STP, 273 kelvins, and we divide by the pressure at STP, which is 1 atmosphere. And the answer we get is 67 liters in that airbag. Let's do one more example. And we're combining all the different methods we've used previously. The last example used grams, and the answer was in volumes. Now we're going to use molarities and volumes of an aqueous substance, and we have a product, which is a gaseous substance, that we're going to calculate how much we produce. All right, so again, you have to get everything into moles. So here we have molarity times volume, which we're going to multiply, although volume needs to be in liters. So we'll use 0.3 liters times the molarity, which is 0.8. So that gives us number of moles, and then we use the ratio of the coefficients. 1 mole of oxygen for 2 moles of hydrogen peroxide, and that gives us the number of moles of oxygen produced. All right, and then we're doing it in 2 steps. What's the volume of the oxygen that's produced at STP? We could be asked it at any other temperature. We're doing STP right now. So volume again would be nRT over P. So we have the number of moles in part 1, 0.12 moles. Put in R. And put in T. And divide by P. standard temperature and pressure. And the answer we get is 2.7 liters. All right, so to sort of summarize what we've been talking about in all stoichiometry, stoichiometry is using reaction equations of the form reactants, arrow, products. Okay, but the reactants may be given in any one of three ways. It might be given in grams, it might be given in molarity and volumes, it might be given in pressures, volumes, or temperatures. Any of those three. And you have to get it to moles. Or you might have to go backwards. So grams will refer to basically any form. You can have grams of gases, you can have grams of solids, you can have grams of anything. Molarity times volume will only be used for solutions, and PV and T will only be used when the substance in question is in a gas form. And then you have products, and you can express products in the same three things: molarity times volume, grams, or pressures, volumes, and temperatures. And again, the same thing is true. Pressures and volumes and temperatures will only be useful for gases. Molarity times volume will only be useful for solutions, but grams can be used for anything. And that's a summary of stoichiometry for everything that we've talked about.